I'll just give a very small snapshot from the range of research and development that's been going on these projects now for over the last 3 years. And just to start out with, I'd like to acknowledge the range of collaborators that have contributed to this body of work: University of Melbourne, New South Wales, BPI, Southern Farming Systems, University of Tasmania, University of South Australia, Sardi and Persa, and my employer, Agriculture Victoria. So what is this work about? Well, effectively, in a nutshell, it's about looking at how we can change subsoils such as this on the left-hand side. So hopefully everyone can see the cursor there, which are sodic, high soil strength. They tend to act like swamps in winter, and then in summer turn to cement. So going from soils like this to subsoils like this on the right-hand side. And as a result of that change in soil structure and other soil attributes, that has the potential to take grain yields. In this case, this is a picture of a canola crop near Balan, just outside Ballarat, where you can look at the control plot there, compared to this plot here, which was a canola where 20 tonnes a hectare of subsoil manuring was applied 3 years previously. So effectively what this means for farmers, I think this picture says it all. There's potential for dramatic improvements in crop productivity as a result of those changes in soil properties. There's just a bit of background of the project, and I'm not sure the range of the audience tonight, so I've sort of have targeted this presentation mainly to grain growers, but I think there'll be interest to a wider audience. Is grain yields throughout large sections of southern Australia can be significantly less than their water or rainfall limited yield potential. And the reason for that sort of rainfall in the Australian environment is always generally the number one limitation to grain yields. And the reason those water limited yield potentials are often significantly below the potential is many of the soils used for cropping contain a range of soil physical and chemical constraints. These constraints can be nutritional, they can be higher levels of salinity, acidity, containing toxins such as high boron, etc. The reason these soil physical and chemical constraints are so important in terms of crop production is generally they limit root growth, and as a consequence the plant's ability to access soil water and nutrients. There's been a range of work undertaken over the last 20 years that have shown the potentially large grain yield responses that can occur to the application, particularly subsoil application of what I'll call nutrient-rich organic matter. A more common term for this is subsoil manuring. This organic matter is typically, it can be manures, it can be composted organic matter, but as a general characteristic, it's a combination of both high carbon and high nutrients, particularly in the case of the animal manures. However, so that's the good news. You know, you'd think, well, we've got this potential to sometimes increase grain yields by 50 to 80%. Why aren't every farmer out there sort of racing out and subsoil manuring their paddocks? And the reason for that is that there's currently several constraints limiting grower uptake of this sort of technology. And these are principally unpredictable yield responses. So what I mean by that is a farmer can go out and invest heavily in subsoil manuring their paddock. One year they may get a 50% yield response. The next year they may get no response whatsoever. So that has really big implications for the financial viability of this technology. There's also some major logistical constraints to the application of technology, and the two principal ones are a lot of the work and research and farm development has been around the use of animal manure-based organic matter, and in some environments, localities, there's ample supply of that manure, where it's be from chicken sheds or pig sheds. But if you actually start doing some back envelope calculations about the amount of manure available throughout Victoria and multiply that by a situation where we're adding anywhere between 10 and 20 tonnes a hectare of manure, multiply that by the couple of million hectares of land used for cropping in Victoria, you've got a significant shortfall in the amount of available feedstock. The other big sort of logistic constraint to a lot of growers is, if you're trying to get relatively large amounts of unconsolidated organic matter, particularly into a subsoil, currently there's just not the ready availability of commercial scale machinery to do it. We've got experimental machinery plant that can do it quite successfully, but we haven't sort of extended that to the commercial scale. And the final one, and it's the major sort of constraint for grain growers in Australia, is at the end of the day, they need certainty that the amount of money and time they invest in implementing this technology, i.e. subsoil manuring their paddocks, they're going to see a financial return on that investment. And it's a pretty simple sum. So I just thought I'd put in this graph. It's from a colleague at University of Adelaide. This graph is applicable throughout the whole Australian grains industry, but particularly through large areas of Victoria. When I talk about soil, physical and chemical constraints, I've outlined a number of them here. So some soils have compacted layers from machinery. Other soils have really dense clay subsoils that occurs quite naturally. If you start going to the areas such as the Mallee, there's high alkalinity. If some of the areas in the high rainfall zone in southern Victoria are very acid, so you have low pH, a lot of aluminium toxicity. You have a range of nutrient deficiencies, not just nitrogen and phosphorus, but also some of your trace elements such as zinc and iron. Those deficiencies occur in both the topsoil and, just as important, in the subsoil. In a range of subsoils, there's a range of what I've called toxicities, and they can be high sodium, boron. There's actually some evidence in highly alkaline soils, high aluminium can be toxic, and particularly in highly alkaline soils, you get bicarbonate toxicities. I'm assuming from the audience tonight around the Macedon Ranges that there's often a lot of temporary waterlogging occurring. And on top of those sort of physicochemical constraints, there can also be sort of biological constraint, and they can be soil-borne pathogens, particularly some of the fungal pathogens, nematodes, and also some deleterious bacteria. And one constraint that's often not recognised is sort of the residual herbicides. I just thought I'd put this map in here. This is, if you look at Victoria, and again, I was probably speaking to a wider audience than just around the Macedon area here, most soils in Victoria, I think it's something like 90% of the soils used for cropping in Victoria is what we call sodic. So sodic means there's a large percentage of the exchange complex is sodium. Some of those soils are saline, but not necessarily. And the reason sodium's so important when you considering sort of soil health and plant production is that it results in, it's a major underlying cause of poor structure. And that acidity leads to a process is what we call dispersion. So if you look at the Petri dishes on the bottom of the figure here, and this is a test that anyone can do in their kitchen. All we've got here is a series of Petri dishes. We fill those Petri dishes with distilled water, or if you want to, you can use tank water, as long as it's not tap water, because tap water can contain chloride and salts that sort of interfere with this process. If you've got a sodic soil, so this soil on the top here is non-sodic, so you add a ped of soil there. There's a test where you can sort of crush it, or alternatively just let it sit there for a couple of hours. That soil is non-sodic or non-dispersive. The water around it will remain clear. However, if the soil is sodic, and as you see I'm moving from the left to the right, that soil is increasingly sodic, what happens is that that soil, it slakes, it disperses, it loses all its structure. And so you go from a soil bed like this, that situation here. And what this means in the soil is, as I sort of outlined before, it basically significantly limits the ability of the soil to sort of transmit water, nutrients, and oxygen. So you tend to get these highly waterlogged prone situations in winter, even after relatively small events of rain. And in summer, as that soil dries out, it tends, because it's got no structure, it sets like rock or cement. And that basically, that sort of property, you end up with crop roots. They're suffering waterlogging in winter, so they can't go into the subsoil. And then when the soil finally does dry out, the soil sets really hard and they can't go down, put roots down to lower parts of the profile. So what this project was about was we're looking at, can we ameliorate soils, and particularly subsoils, with this nutrient-rich organic matter? And if you looked at particular constraints in Victoria as outlined, but they tend to be based around soil structure, nutrition, and also toxicities. And when we first started this project, we did a series of glasshouse work. This is some pictures from colleagues in Wagga, southern New South Wales. Basically what these overhead sort of watering systems, so we can drip irrigate long cores. The cores are 60 centimetres deep. And what we try to do is basically recreate what would happen in natural soil profile. So normally the top 10 centimetres of soil is non-sodic. You tend to start getting intermediate layers from about below the plough layer, so below 10 centimetres, where you've got moderate level sodicity. So I'll often tonight will just refer to sodicity, or exchangeable sodium percentage. That's what ESP stands for. And I just want to keep in mind, if you've got an ESP greater than 6, that soil under Australian conditions is classified as sodic. And then once you start getting down in the subsoil, often that ESP levels can be greater than 20 and sometimes up to 30 or 40 units. What we've been doing in these initial experiments, we looked at putting narrow sausages of different emollients. It could be gypsum, or it could be nutrient-rich organic matter such as manure. And what that work found out, we had a number of sort of simple findings from that work. The first one was, generally crop dry matter responses tend to increase with increasing rate of application of these nutrient-rich organic matter. So what that means under field conditions, you're often requiring rates between about 10 and 20 tonnes a hectare.
Hello, we seem to have just lost Roger for a second.